and we're excited to hear her tell us about dental pulp inflammation. So take it away, Jia. Thank you.
Good afternoon, everyone. So thank you for joining me today. My name is Jia Huang, and I'm currently working with Dr. Shimizu. I'm a PhD student in IQTrack. So today I am excited to share my research on HDAC6 inhibition and its potential to transform how we manage dental pulp inflammation. So okay, let's begin with a very stark reality: dental caries. So dental caries is one of the most prevalent chronic disease worldwide. And in the US, by the age of 20, a staggering 90% of adults have experienced at least one cavity. And of this, 26% will progress to irreversible pulpitis, which is a painful inflammatory condition where the pulp becomes irreversibly damaged. And for younger patients, this is particularly devastating because immature permanent teeth relied on a vital pulp to complete root development, and losing that vitality compromising the tooth structural integrity, longevity, and even the patient's quality of life. So the current standard of care for irreversible pulpitis often defaults to root canal therapy, RCT, which is shown on the left. So while effective at removing infections, RCT sacrifices many remaining pulp vitality, leaving the tooth in it and more prone to fraction over time. And for a young patient, it is let's say 15 years old with immature tooth, undevelopment root and open apex. This isn't just a clinical decision. It is a lifelong compromise. And this is why vital pulp therapy, VPT, has emerged as an alternative choice. So vital pulp therapy aims to preserve pulp vitality through minimum invasive techniques like direct pulp capping or pulpotomy. And when successful, it allows the pulp to heal, promote continued root development, and maintain the root's natural defense mechanism. However, and this is a critical point, the success of vital pulp therapy hinges on two factors: controlling inflammation and activating the pulps in its regenerative capacity. But here's the question: what mediate these processes? And the answer lies in the only interface the remaining pulp tissue interact with, which is the pulp capping material itself. And this material isn't just a passive barrier. It becomes the gatekeeper of the pulp's microenvironment, and it must simultaneously suppress destructive inflammatory signaling and create a bioactive niche that stimulates odontoblasts, stem cells, and immune cells to collaborate and repair. So if the material fails at either test, inflammation will persist, regeneration will stop, and the pulp vitality is lost. So this brings us to the material we currently use today. Let's evaluate how they measure up. And for decades, calcium hydroxide was the gold standard. It is alkaline, which help neutralize acidic environments caused by bacteria, and it stimulates reparative dentin formation. But it has significant limitations. The reparative dentin it forms is porous and poorly organized, and often with internal defects that allow bacterial micro leakage. And its mechanic strength is subpar, and it doesn't reliably seal the pulp. And empty on the right, the mineral trioxide aggregates improve upon this, and this is biocompatible and forms a better seal, and it stimulates more consistent dentin bridging. But here's the problem: the MTA still primarily promotes reparative dentin, which is a disorganized A-formous matrix, rather than regenerative dentin, which mimics the natural tubular structure of this primary dentin. And more importantly, neither calcium hydroxide nor MTA directly addresses the inflammatory cascade that already raging in the pulp. And imagine this, you are capping an inflamed pulp with MTA or calcium hydroxide, and the material creates this physical barrier and encourages dentin formation. But beneath that barrier, pro-inflammatory cytokines like IL-6 and TNF-alpha are still flooding the tissue, recruiting more immune cells and perpetuating a cycle of damage. It is like building a roof on a house that is already on fire. You might protect it from rain or snow, but the foundation is still burning. And this is a critical gap in our current approach. We lack therapies that simultaneously suppress inflammation and creates this pro-regenerative microenvironment. And without resolving the inflammation, even the best biomaterials cannot optimize healing. So how do we bridge this gap? One of the promising avenues lies in the use of epigenetic modulations. So epigenetics, which is the study of reversible modification of DNA and histones that regulate genes expression, has already shown significant potentials in areas like cancer therapy and immunology. Now it is emerging as a promising approach to address challenges in dentistry. So one promising target that we're focusing on is this histone HDAC, histone deacetylase 6. But let me give you a little bit background about this HDAC first. So HDAC stands for histone deacetylase that removes this acetyl group over here from both histone and non-histone proteins, and they involve in controlling the activity of genes within our cells. So to understand how HDAC inhibitors works, let's think of genes as a tiny instruction manuals that tells your cells what to wear and what to do. So the activities of genes can be influenced by certain chemical modifications, and one of these modifications is called acetylation, like this yellow tag over here. And HDAC enzymes, the pink one, will remove these acetyl groups from the proteins around which genes are wrapped and causing the genes to become less active or switch off. And now here's where HDAC inhibitors comes in. HDAC inhibitors, they're like this little helpers that blocks the action of the HDAC enzymes. And by doing so, they allow the acetyl groups to stay attached to the proteins and keep the genes active or switch on. And this ability to regulate gene activities is important because different genes control various functions in our bodies. And by using HDAC inhibitors, scientists can potentially influence the activity of specific genes that are involved in disease like cancers or inflammatory disease or neurodegenerative disorders. And this ability to regulate gene activity has not only shown promise in the medical research, but also in dental fields. And dental research have recognized potential HDAC inhibitors to target specific genes involved in different dental processes, especially mineralization processes involved in healthy dental pulp cell population. And despite all these findings, they emphasize the significance of epigenetic regulation through HDAC inhibitors. There are still a few gaps in the field that my research is seek to address. So the first gap in the field, which is probably the most important one, is that there is still a need for further research to understand the anti-inflammatory function of HDAC inhibitor in dental pulp cell populations. All of the previous studies focus on healthy dental pulp cells, not inflamed ones, but almost all the dental pulps that we deal clinically on a regular basis are to some degree inflamed. So this knowledge will be crucial for translating these findings into future clinical practice. And the second drop in the field is the molecular mechanism of how HDAC inhibitor calms and inflame dental pulp cells and macrophages is still unknown. So my work is seeking to address both of these gaps. And to test this, I used two models, human dental pulp cells challenged with E. coli LPS and mouse bone marrow-derived macrophage exposed to P. gingivalis LPS. And I hypothesized that HDAC6 inhibitor by inhibiting that using a selective HS6 inhibitor next to Restat-A would reduce NF-kappa B activation and rebalance cytokines. So first, to evaluate the effects of Nextras-A on the inflamed human dental pulp cells, proliferation, and migration. So we performed this scratch wound healing assay. And the assay mimics the natural process of wound healing. Like after pulpotomy, there will be an actual wound on pulp tissues where dental pulp cells need to migrate to close. And here's how we did it. We first seed human dental pulp cells to form a monolayer cell sheet, and then we treat the cells with either SAHA, which is a pan HDAC inhibitor, or Nextras-A, which is a selective HS6 inhibitor, and E. coli LPS. And right after we're adding the drugs, a small scratch will be made in the cell layer using a pipette tip. And this scratch mimics a wound in the pulp, in the dental pulp. And after creating the scratch, we took pictures of the scratch at 0 time points and 24-hour time points to track the healing process. And by analyzing these pictures, we can calculate how quickly they close the wound. And the scratch wound healing assays would not only help us to understand how inflammation affects human dental pulp cell migration, it also provides some insights into how Nextras-A and SAHA affects the inflamed cell movement and wound healing. And this is the result. So interestingly, when we expose the cell to E. coli LPS, so when we look at this, this line is 0 hour time point, this is 24-hour time point, and this column is LPS treatment group. We found that their migration was reduced compared to control group. So when we treated the cells with Nextras-A, which is a HS6 inhibitor, or SAHA pan HDAC inhibitor, alongside with LPS, their migration ability was fully restored to levels similar to control groups. And the HDAC inhibitors seems to counteract the negative effects of E. coli LPS on cell migration. So we then performed the gene expression analysis to identify and quantify the expression level of NF-kappa B target genes. This was done by real-time qPCR. And by comparing these gene expression levels in cells with and without HDAC inhibitors, we can determine whether these drugs can cause any change in expression of inflammatory-related genes. And still, we are using the 3-hour HDAC inhibitor pre-treatment plus the 3-hour inflammation substrate treatment. And then we'd extract the mRNA from the cells and perform real-time qPCR. So the results shows that in human dental pulp cells, the pre-treated with Nextras-A, HDAC6 inhibitor, and SAHA pan HDAC inhibitor leads to this significant decrease in the expression of two genes, MCP1 and IL-6. So the green bar is a selective HS6 inhibitor, and the orange bar is the pan HDAC inhibitor. But when it comes to IL-1 beta, we do not observe any significant changes among the groups. So this result is not aligned with previous research. I think it can be explained by biological variability because we're using primary cells, and the cells from different donors or passages may act differently. Okay, so this findings indicates that Nextras-A and SAHA can specifically target and regulate expressions of certain inflammatory genes in human pulp cells, but they may not have the same impact on all genes involved in inflammation. And although we observe this significant difference of this gene expressions, the fold change is not very high, as we can see. The nextrostat can only go up to 5-fold. So for this low level of gene expression, we may not. This may not result in a significant change at the protein level, so we will not perform protein level experiments on human neutrophil cells. As for mouse bone marrow derived macrophage, we also want to see if they respond differently to different types of LPS, like in previous research we observed in human neutrophil cells. So we stimulate the cells with PG-LPS and E. coli LPS, and we found that both E. coli LPS and PG-LPS can significantly increase the expression of IL-1 beta and TNF-alpha genes. So unlike what we observed previously in human neutrophil cells, the PG-LPS actually works fine on mouse macrophages. So that's why we chose PG-LPS to stimulate the mouse macrophage later in the experiment. So we also find that both the green bar and the orange bar, the nextrostat and SAHA, were able to decrease pro-inflammatory IL-6 expression while maintaining a relatively high level of anti-inflammation IL-10 expression. And both E. coli LPS and PG-LPS challenge macrophages, indicating this shift towards an anti-inflammatory state. And also the fold change is pretty good, it's pretty high. So we proceed to confirm the correlations between the gene level expression change and the protein level changes. We use ELISA to measure the levels of two proteins, IL-6 and IL-10, in mouse bone marrow derived macrophage. And by measuring the level of IL-6 and IL-10 proteins, we aim to determine if there were any significant differences in protein production among the experimental groups, which would help us to understand the potential therapeutic effects of nextrostat A. So same here, we did a 3-hour treatment. And at 6 hour, we used this supernatant for ELISA. So our result shows that when the cells were stimulated with PG-LPS alone, the production of IL-6 protein significantly increased compared to the control group. However, when the cells were pre-treated with nextrostat A and SAHA, the production of IL-6 protein remains low and is also similar to control groups. And we also observe no significant difference between IL-10 between the groups treated with LPS and the groups pre-treated with nextrostat A or SAHA followed by PG-LPS. And these findings were consistent with our earlier qPCR results. And so overall, our ELISA results confirm that nextrostat A and SAHA pretreatment could regulate mouse macrophage to give a more balanced and controlled inflammatory response. So after confirming the anti-inflammatory effect of this selective HF6 inhibitor, is almost as good as the pan-HDAC inhibitor, we then are interested in understanding the mechanism of nextrostat A. So we then perform this immunofluorescence staining on mouse bone marrow derived macrophage to visualize the whole process and the location and even the distribution of inflammatory markers and molecules involved in the inflammatory response. So in our experiment, we chose to stain for a protein called P65, also known as NF-kappa B P65 subunit. The reason why we choose this P65 protein is that first, NF-kappa B is the central player in the activation of inflammation-related pathways, and the P65 subunit is a major component of the NF-kappa B complex, and it is involved in its activation and translocation to the cell nucleus. So this is the NF-kappa B signature pathway of the cells. As I mentioned just now, the NF-kappa B is a protein complex family that plays an important role in inflammation. And one of this main form is made up of two subunits called P50 and P65. And they form this heterodimer and remains inactive in the cytoplasm. When NF-kappa B pathway is activated either by LPS or TNF, an enzyme called this IKK is involved, and this triggers a series of events. The I-kappa B protein, which I-kappa B protein is here, which normally keeps the NF-kappa B inactive, gets phosphorylated, as shown this green little p over here. It gets phosphorylated and marked for degradation, and it releases the P50 and P65 dimer from the inhibitory complex. And additionally, the P65 interact with impurine protein. These impure proteins act like a transporter vehicle and help this P65 enter the nucleus. And inside the nucleus, the P65 will perform its important task by binding to a specific sequence of DNA in target genes, most likely inflammatory genes, and control their activation. So when it's time for P65 to leave the nucleus, an export protein is bind to I-kappa B that binds to the P65 and form this complex that exit the nucleus and return to the cytoplasm. So this is the back and forth movement of P65. So in summary, the nuclear translocation phenomenon of this P65 protein is mainly caused by this activation and phosphorylation. So by staining P65, it helps us to correlate functional outcomes from the wound healing assay and all these genes, inflammation genes calm down with the specific inflammatory markers, in this case, the P65 or pathway, which is NF-kappa B pathways, to strengthen our overall conclusion. So here's how we stain a P65. We first see the mouse macrophages, and after the cell detachment, we treat the cells with either nextrostat A or SAHA for 3 hours, and then adding TGLPS for treatment another 3 hours. And at 6-hour time point, we fix the cells, and after that, we use antibodies that can specifically bind to P65 proteins. And these antibodies are labeled with fluorescent dyes that emit this green color. And then I count the numbers of P65 possibly stained nuclei and divided by the DAPI stained total number of nuclei to obtain the percentage. So what we found was that when the cells were treated with inflammation substrates, the P65 protein will move into the nucleus. As we can see in here, the nucleus are light up. Comparing to the control groups, the nucleus are hollow circles. But when we treat the cells with nextrostat A or SAHA before the stimulation, before the LPS stimulation, the translocation of the P65 protein was significantly reduced. So we can see in here the nucleus stay hollow and unstained. So this suggests that both nextrostat A and SAHA have the ability to either to prevent the P65 from getting into the nucleus or fasten P65 proteins getting out from the nucleus. And as we see the prevention of this P65 accumulation inside the nucleus, we speculate whether the suppression of P65 nuclear accumulation is a key mechanism underlying nextrostat A's anti-inflammatory effects. And we're still working on the human dendritic pulsar part. So some conclusions with this nextrostat work. We investigated the effects of nextrostat A, which is a potent selective HDAC inhibitor 6, HDAC 6 inhibitor, on human dendritic pulse cells and mouse bone marrow derived macrophage in the context of inflammation. So using wound healing assay, our result shows that Nextran-SAT-A seems to counteract the negative effects of E. coli LPS on human adult cell migration. Then we next review that the pretreatment of this Nextran-SAT-A can regulate the expression of gene involved in inflammation and have protein level impact on immunoreaction. And furthermore, our data demonstrate that HDAC6 inhibit Nextran-SAT-A significantly reduce nuclear translocation of NF-kappa B P65 protein in inflamed macrophages. So in essence, HDAC6 inhibitor would act as a dual action therapy, calming the inflammatory storm while creating this microenvironment conducive to regeneration. And for a patient with irreversible pulpitis, this means that we might one day pair MTA with a topical HDAC6 inhibitor to not only seal the pulp, but also reprogram its inflammatory response, turning a hostile environment into a healing one. So before I open the floor to questions, I would like to thank my incredible team, Dr. Yoshi, our collaborator, Dr. Duncan, and of course my PI, Dr. Shimizu, everyone in the oral department. Thank you, and if you are not in this pics, don't blame me, blame Google. A special shout out to thank you, Dr. Keshlani, for inviting me to speak today. It is truly an honor, and thank you all for your attention. I'm happy to take any questions now.
Thank you, Gia. Very nice job. Dan, your question.
Oh, yeah, that's a great talk, Gia. I have a couple of questions about the sequence of events. So do you add the LPS first or after you've added the SHA, SAHA, or the NEXA?
So it's like this. We add the HDAC6 inhibitor pre-treated for 3 hours, and then we add the LPS.
Okay.
And we choose to do this because this will give us a better idea of exactly how the drugs works. We will pre-expose the cells to the drugs. It's not a perfect model because in real situation, we know the inflammation comes first and then we do the treatments. We want the drugs to kick in to control the inflammation. But because now we're working on try to study whether it has this anti-inflammatory ability, and we want to work on the MOA of these drugs. So that's why we chose to pre-treat the cells first.
So also let me follow up. Do you have any idea as to whether or not the SAHA or the NEXA interact with LPS as opposed to the cells?
For now, we're the MOA of these two drugs will mainly act on cells instead of LPS. It's not binding the LPS.
Okay. So, well, do you know that for sure? Or, I mean, obviously, that would be your hypothesis, but have you tested them independently, adding just the LPS to the SAHA or the NEX to see if, in fact, they are interacting with those drugs as opposed to the inflammatory cells?
I believe in our preliminary experiments, we mix these two drugs and then add to the cells. And yes, and it's doing nothing to the cells. The cells are not inflamed.
Oh, okay. So, and the other question, just technically, have you looked at a dose-related response, either using different doses of LPS or different doses of your drugs?
Yes.
I know this is early, so I'm just asking.
Yes, we have tried different doses of this HDAC, and an even higher dose might cause some will inhibit the cells too much. Will have the cell toxicity, so that's why we chose this specific concentration. And like too high of LPS concentration will also damage the cells, will cause the cells to die too quickly before the drugs can do anything.
In our experiments, we've done some comparison between LPS extracted from PGAA and E. coli, and we found out that, at least in our hands, the LPS from the oral organisms is more potent than the commercially available E. coli endotoxin. So
Yeah,
I don't know
exactly.
if
Yes, which one? Yes, actually, there are experiments studying like exposing the human netral pulp cells to E. coli LPS and PG LPS, and we'll also treat our cells with this too. It looks like our cells, well, at least this batch maybe, our cells react more like more potent to E. coli LPS instead of PG LPS.
interesting.
So unlike macrophage will react to both. They respond very obviously to those LPS, different kinds of LPS. So yeah, we did treat the cells with different types of LPS and pick the one that's more potent.
Okay, thank you. Thanks very much. Great job.
Thank you.
Very nice. Any other questions? You can just turn your microphone on if you have a question. All right. If not, have a good weekend, everybody. Gia, thank you so much. Wonderful job. We
Thank
look forward to hearing your progress each
Yeah,
year.
great job.
Thank you.
Thank
Great
you.
job.
Great
Good
job.
weekend, everybody.
Yeah.
Thank you. Have a good weekend.
Thank you.
Thank you.